In this video, we're going to take a look at finding Laplace transforms of functions defined using step functions. Here are the two formulas we'll be using. The derivations of those formulas can be found elsewhere. We may go through the second one in class, but they certainly, the second one can certainly be found in any textbook addressing this topic and in several videos that you can find on the internet. What I do want to point out is that the first one is simply a special case of the second. If our f of t in the second one, if f of t was simply the function 1, then the Laplace transform of that is 1 over s. And so you can see we can rewrite the first formula as e to the minus cs times 1 over s. And so it actually has the same form as the second one, but for the particular, again, for the particular function, little f of t equaling 1. So let me get rid of part of that. Let's get rid of this portion down here. And let's look at a particular example applying the second formula. So probably what we want to do first here is identify our value c, and to do that we go to our step function and we look right here. So we can see in this case that c equals pi over 2. Now we're fortunate in that in this case that we have the same value here with our little f function as well. There will be times when those two may not agree and we'll have to do some manipulation on the function little f in order to get it to have the same shift as our step function. But in this case, c equals pi over 2. So then from that, what we have is that t minus c is t minus pi over 2. So the t minus c portion of these two functions is this which I'm underlining in red. And those correspond to the parts in the formula above that I've underlined in red as well. So what we have to do now is identify the function little f, and we can see the little f in this case is this part right here. It's the cosine of 2t. So little f of t equals cosine of 2t, and the capital F of s here in the formula that I just double underlined in red is simply the Laplace transform of the little f. So the Laplace transform in this case is the Laplace transform of cosine 2t, which is s over s squared plus 2 squared, or plus 4. So there's our capital F of s. So now all we have to do is put the pieces together. We can see the Laplace transform, let me circle it in blue up here, is e to the minus cs times our capital F of s. So the Laplace transform that we're after in this case is e to the minus pi over 2 times s, and then times our f of s, which is s over s squared plus 4. And of course, if we wanted to, we could write all that a little bit differently. We could write it as s times e to the minus pi over 2 s over s squared plus 4. So that's a pretty basic application of our formula for the Laplace transform. Now we'll look at a slightly more challenging situation. So again, here's our formula that we want to be using. I'm going to rewrite it in slightly differently using the more compact notation for u, which is going to save us just a little bit of room because we're going to look at a moderately long function here. And so it'll save us some room horizontally. So let me move that other formula up out of the way, and let me write down the function that we're going to be looking at. So here's the function we're looking at, and if you look at this first part, you can see that things look good there because the 2's we have a t minus 2 in our function, and we have a u sub 2. So these c's have to match right here, and we do have a match. Let's see, let me erase these blue lines, and you can see that we have a match right here as well. But if you look at the second part, we don't, or at least it doesn't appear that we have any such match. So there's some kind of a problem over there, but you'll see that things are going to work out pretty nicely. Let's rewrite that. You can see that that there's a factor of 2/3 in both parts of this right here. And so I can factor the 2/3 out, and in fact I'm going to factor out negative 2/3 to make the t be positive. So when we do that, the result that we get is this. And you can see that sort of magically we end up getting the same values here. And that kind of surprised me the first time I did that. I'm not sure exactly why that happens. I should look at a few more examples, but I'm pretty certain that this will always happen when we deal with this particular type of function, which you may recall was represented a ramp function like I've drawn in this little picture right here. So I think anytime we're doing one of these ramp functions, we'll get things to work out in this manner. Now let me get that graph off of there. And so you can see that we're now ready to take the Laplace transform. So we need to apply the above formula. If we look at the first part, the value of c is 2. So I'm looking at just this part of our function here. We have c equals 2. And what is f of t? Well, f of t could be thought of as 2/3, but or 2/3 t. In fact, let's just do that, 2/3 t. And so f of s then, capital F of s, remember the transform of t is 1 over s squared, so that'll just be 2 over 3s squared. So that takes care of that part. We know our c and we know our f of s. And if you look at the second part, it's exactly the same, except that c in this case is 5, and I guess we would say little f of t is actually negative 2/3 t. So our capital F of s in this case is the same as the other one, but it's just negative 2 over 3s squared. So now we can go ahead and put together the transform of h. So the transform of h, which we'll denote by capital H of s. We just have e to the minus cs, so that would be, in this case, for the first part, e to the minus 2s, times our f of s, which is 2 over 3s squared. And then for the second part, we have e to the, so let me add, we've got plus e to, so let me go on to another. For our last example, we're going to, in this video, we're going to look at this function, which you may or may not recall. It was the equation for the function that had value 0 up until time 1, and then it was the function t minus 1 quantity squared, so it was a parabola rising up until time 3, and then we had the constant value 4 after that. So that's the graph of the function, and in this video what we're going to do is find its Laplace transform. So let's get the picture off of there, and let's go ahead and take a look at finding the Laplace transform. The first thing we need to do is regroup the terms here in order to get one term that has the u of t minus 1 and another term with the u of t minus 3. So when we do that, what we get is this. And if you don't see how that comes about, you might just pause the video for a moment and run through the algebra yourself. Now if we look at what we have, you can see we have a nice situation here where these both have a shift of 1. Both our function t minus 1 squared, that's really just t squared shifted by 1, and that matches the shift on the step function there. But over here we have a 3, and there's no 3 anywhere to be seen in this other part. So what we're going to have to do is we're going to have to do a little bit of manipulating with that t minus 1 squared quantity minus 4. So let me show you what we'll do there. So first I rewrite the t minus 1 as t minus 3 plus 2. My motivation for doing that is that we have this 3 up here that we're trying to match. So next what I need to do is take a look at that quantity inside the square brackets. And let me just put something in here in red. If we have a quantity a plus b all squared, so in our case the a is the t minus 3 and the b is the 2, that's equal to a squared plus 2ab plus b squared. So thinking of the 2 minus 3 as a, this is a, and the 2 is b, what this then turns into is the following. We have t minus 3 squared, that's the a squared term. Here there's a 4 because b has the value 2, so a times b is 2 times t minus 3, and then we double that to get 4 times t minus 3. And then b squared is 4, and then we still have the negative 4 sitting there. So the 4 and the negative 4 cancel each other. And so what we're left with is t minus 3 squared plus 4 times t minus 3. So let's transfer that back into our function f and see what it looks like now. So what we have now is this that you see here, and you can see now we have a 3 here, here, and here. So we now have that match that we were looking for with our step function in that place. So now what we need to do is analyze each piece of this separately. So let's take a look. We have a piece here, which in this case what we have is we have our little f of t. Now this is not the same as the little f being used over here for our function. So ignore that in the circle for a moment. And what we have is a little f of t equaling t squared. And then we have a translation of that. So we're really we have here the t minus 1 squared is little f of t minus 1. And we have a c value of 1. If we look at this other part, our little f in this case, little f of t, is t squared plus 4t. And then we're doing a translation of that by 3. So our c value in this case is 3. So then, if we apply the Laplace transforms for those two parts, what we end up getting, let's see, our Laplace transform of f of t for this first part, the Laplace transform of t squared, so our capital F of s for that part will be 2 over t cubed, or s cubed, excuse me. And then for this second part, our capital F of s, again the t squared becomes 2 over s cubed, and then we have plus 4 over s squared. And so now what we can do is we can put those pieces together to come up with the actual capital F that we're looking for. So that's from here. So now capital F of s is what we get by putting this first piece together. Let me circle that in blue. So that information, applying the formula for the Laplace transform with a step function, gives us e to the minus 1s times 2 over s cubed. And then we have this minus sign comes down. So we have minus. And then we have e to the minus 3s times the quantity 2 over s cubed plus 4 over s squared. And we could do some simplification of that. I don't know that there's any point to that necessarily. We could write, you can see we have a 2 over s cubed, so we could write 2 over s cubed times the quantity e to the minus s minus e to the minus 3s. And then we can distribute that e to the minus 3s into the other part, so then we have minus 4 over s squared e to the minus 3s. So that would be another way to write our transform. But that shows how to get the transform in a situation where we need to make a translation of our function that matches our step function.